Hello and good day, everyone. I'm Mohd Zamir Pakhuruddin from University Sains, Malaysia. So I'm currently serving as a senior lecturer at University Sains, Malaysia in Penang. So today I'll be sharing with you about solar cells. So this is the outline of my lecture. So I'm going to start with a little bit on my background, and I'm going to give you some introduction to solar cell, followed by physics of solar cell, and I'm going to share with you photovoltaic technologies that we have now in research phase and also in the market. And finally, I'm going to end by sharing with you opportunities for chemistry students related to photovoltaics. So I did my PhD in the University of New South Wales in Sydney, Australia. So I did my PhD in PV engineering, graduated 2016, and I graduated from electrical engineering from the University of Sheffield back in 2003. So it was a long time ago. So before joining academia, I spent about 7.5 years altogether in semiconductor industry and hard disk drive industry in Malaysia. So I spent about 6 years in Silterra as a senior photolithography engineer, handling photolithography process and equipment, and then another 1.5 years in Fuji Electric in Malaysia as well, handling sputtering process R&D. So now I'm handling a research group called Photovoltaic Materials and Devices, or we call it PVMD. And in our group now we have a couple of PhD students, MSc students, and also a final year project students or FYP students. So now our current focus is on black silicon solar cells, perovskite solar cells, organic solar cells, and we do evaluation or R&D for various types of applications. For example, for solar windows, for conventional solar cells, for applications in large-scale solar farms, for indoor photovoltaics, which is a new field coming up in the field of photovoltaics. And also we do some simulation by ray tracing, for example, in order to optimize the optics in the solar cells. So one picture for my research group that I'd like to share today. So far I have PhD students in progress and another one joining next semester. So I have 3 MSc students, MSc by research, and then a few of FYP students working on solar cell as well. So let's get started to introduction to solar cell. So just to let you know that now in a single hour, the amount of power that we have from the sun that strikes the surface of the earth is more than the entire world consumes in a year. So if we can harvest 100% of the incident power from the sun every single hour, so the power will be enough to power the entire world for a year. So unfortunately, the technology that we have at the moment is not enough to do so. So the potential from the sun, potential from the solar power is huge, is immense. It's a matter of optimizing the right technologies and deploying the right technologies in order to harvest the solar power. So solar cell is also called photovoltaic effect. So the name goes to the conversion of sunlight to electricity. So that's called photovoltaic effect. So when we talk about PV effect, it's concerning conversion of sunlight to electricity. So the photo part in the photovoltaic goes to the photons, which makes the sunlight, right? Sunlight is made up of photons, and the voltage is due to the voltage generated across the solar cell during the illumination process. So we illuminate the solar cell with sunlight, and then we expect to generate electricity out of it in the form of current and voltage. So that's how a photovoltaic effect is obtained, right? The name. So even though we have the very first observation of photovoltaic effect back in 1839 by a scientist called Edmond Becquerel, a French scientist, the first practical solar cell was only available back in 1954. Okay, back in 1954 in Bell Lab, right? So this is the first practical solar cell realized with 6% of conversion efficiency. So by these three guys you can see in the picture, Gerald Pearson, Daryl Chapin, and Kelvin Fuller. So on the right hand side you can see the measurement is done in order to determine the output or the electricity generated by the solar cell fabricated in the lab. So you can check out the source included down here in the PDF file by NREL in order to see, in order to understand the full story of the breakthrough. Right, so why PV? Why PV? We have a couple of reasons. The obvious reasons, I would say. The first one is sunlight is abundant, so we have sunlight forever, right? So we will never be finished of sunlight. Sunlight or solar power is a clean energy source. We don't have any pollution out of it. We don't have CO2 emission. And the technologies that we have for PV conversion gets more efficient over time. I'll show you how does it look like since our very first data back in 1976, documented by NREL, or National Renewable Energy Laboratory in the US. I'll show you that in a moment. And we also have consistent reduction in technology costs, which is used as the benchmark to measure the viability of a technology in PV. So it's normally calculated in US dollar per watt. And later on, I'll show you how the technology cost has evolved over the last 50, 60 years until 2020. So this is our solar spectrum. So we normally see solar light or sunlight every day, but I'm not sure whether you have ever looked at this solar spectrum. So on the right hand side, you can see our solar spectrum. We call it AMS 1.5G solar spectrum, which is composed of 3% of UV, 40% of visible, 45% of visible light, and then 52% of infrared. So we have a quite broad range of illumination. So if you look at the spectrum, here, the peak of the solar spectrum is in the visible region. It's in the visible region here. So if you look carefully, the peak is somewhere around 600 nanometer. So that's where you want to optimize in order to harvest as much sunlight as possible in your solar cell, right? So when we do our measurement of conversion efficiency on any solar cell, we normally have to use a standard called standard test condition, or STC. So this condition consists of AM 1.5G solar spectrum or AM 1.5 global solar spectrum, which consists of specular light and diffuse light. So we also have another two called AM 1.5D or AM 1.5. The other one is one is for global and one is for diffuse, right? One is for global, one is for diffuse. But for the sake of standard test condition, we need to use AM 1.5 global solar spectrum. The illumination power has to be 1000 watt per meter square, and the measurement has to be done at 25 degrees C. So these are the three conditions that are used in standard test condition in order for us to know the standard conversion efficiency of our solar cell. This is crucial, especially if you want to declare that your new solar cell, for example, or your solar cell based on new material or new technologies or new device architecture. If you want to declare your solar cell with a new world record, you need to base on STC, and it even has to be confirmed by certified labs across the world. For example, we have NREL in the US, we have a couple more in the Europe, a few more in China, for example. So the new solar cells have to be certified at STC by certified labs in order to be in order to appear on the new world record chart that I'm going to show you later on. Okay. So solar cell, how does it look like? Solar cell, if you dissect, if you do a cross section of a solar cell from the side, you can see that solar cell composed of a couple of layers. So solar cell essentially is a p-n junction device. So when I say it's a p-n junction device, the solar cell has to have a semiconductor of a p-type paired with semiconductor of an n-type. Okay, so p and n semiconductor makes a solar cell, right? So why do we need to have a p-n junction? A p-n junction is there to do carrier separation. The moment we do a generation of carriers, I'm going to show you later on, the carriers, positive and negative charge, or electrons for the negative charge, and holes for the positive charge, need to be separated at the junction and collected at the metal contacts in order to produce electricity. So you can see a couple of layers in the cross section of the solar cell. So the first top one here is a layer that we call AR layer, or ARC, anti-reflective coating. So the role is to minimize broadband reflection from 300 nanometer to 1100 nanometers, so that the solar cell reflects as minimum light as possible. So that's what we want from a solar cell. You want to minimize reflection from the solar cell. You don't want to have high reflection from the solar cells, because the reflection will translate as an optical loss to the device, right? The second layer here is N+. N+ is what makes a p-n junction. So this is the N side of the solar cell. So where you diffuse phosphorus, for example, or arsenic, or if you look into your periodic table, so you need to diffuse group 5 materials, group 5 elements into the silicon in order to produce N-type, or negatively charged semiconductor. So you also have a front metal contact here, illustrated by these two metal lines on top, in order to be the negative contact for the solar cell. Then you have a p-type silicon here. P-type silicon represents the p side of the p-n junction. So this is usually represented by the whole bulk of the silicon wafer. So that is diffused with a very thin layer on the front side to make the n-type in order to form the p-n junction. Then at the back here, you also have a local aluminum back surface field in order to minimize carrier recombination at the back. And then we have a rear contact at the back to be your positive contact. Sorry, to be a positive contact. So in essence, we have a p-n junction in the middle, and then we have ARC on the front, a BSF at the back, and we have two sides of the metal contacts, the negative side on the front side and the positive side at the back side, in order to collect the carriers. And the P and N side can be switched accordingly, according to your technology. So for example, if you are working on a p-type solar cell, then your wafer here has to be p-type, and your emitter on the front side has to be n-type. And on the other hand, you can also use n-type silicon wafer with a p-type diffuse emitter on the front side, and your contact will be switched as well. So your front side is using p-type or positive contacts for the p-type emitter, and negative contact at the back for the negative wafers, for example. So in order to do the generation of the electricity by the sunlight, or PV effect, there are 4 steps that need to happen. So the first one is absorption of light from the photons, or from the incident light. So to be able to absorb the light from the photons or from the sunlight, so your semiconductor they use, for example, if you use silicon, the semiconductor has a band gap of 1.12 for silicon, 1.12 electron volts. So to be able to absorb the incident light, the photons, the incident photons, have to have energy above above than or equal to 1.12 electron volt. Okay, so if the photons do not have energy above or equal to 1.12 electron volts, the photons will not be absorbed, and they will be transmitted through the solar cell as a loss in optics. Okay, so once the photons are absorbed, we will generate electron hole pairs in the semiconductor. So every incident photon will generate one electron hole pair in the semiconductor. So generation here means the valence electrons in the valence band, if you learn about energy gap, so the valence electron in the valence band at the bottom will be excited into conduction band on the top side in order to be free for conduction. So that's what we call generation. At the same time, when we have excited electron in the conduction band, we'll also generate free holes in the valence band for the conduction as well, right? So the moment electron hole pairs are generated, so these electron and hole pairs need to be separated by the junction. So you can see here in the illustration, you can see electron hole pair. For example, electron in the red color and hole in the blue color. So these two electron and hole need to be separated by the p-n junction, where the electron will be going into n side, in this case to the front side, to be collected by the front contact, and the hole need to be going to the back side to be collected by the rear contact. Okay, then the electron and hole will be going through the outer circuit to complete the circuit and to generate the electricity. So this is what you will see if you do the measurement of IV curve on your solar cell. So you will have a curve like this. So I'm going to explain later on what does it mean by this curve. So it's going to look something like this. So this shows generation of electricity upon illumination on the solar cell. So what does it mean? So the curve is given by equation I equals to I naught exponential QV over nkt minus 1 minus IL. So I naught is the saturation current density or the leakage current. Q is the electronic charge. V is the voltage. N is the ideality factor. K is the Boltzmann constant. And T is temperature. And IL is the load current generated. Okay. So from this curve, you can extract a couple of important parameters in order for us to calculate conversion efficiency of the solar cell. So if you look at the first curve on the top left, so the intersection between the curve to the y-axis is called short circuit current, or IC. On the x-axis here, the intersection of the curve with the x-axis is called VOC, or open circuit voltage. And another important parameter is called field factor. You can see at the bottom curve here. Field factor gives the squareness of the curve. So ideally, you want to have a perfectly square curve like that. This is the y-axis. This is the x-axis. You want to have a square curve perfectly. But due to the nature of the solar cell and limitation in the solar cell, we can only generate something like that. So which is limited by the resistances in the solar cell, namely parasitic resistance, right? And consists of series resistance and shunt resistance. And this field factor is given by the ratio of Imax times Vmax over IC times VOC. Okay, so that will give you field factor in the form of percentage. So in order for us to calculate the conversion efficiency of the solar cell, so we need to use this equation where VOC times IC times field factor over input power. So this is referring to the 1000 watt per meter squared that we've just discussed in the STC, or standard test condition. Then times 100%, then we can come up with the conversion efficiency of the solar cell. So when we talk about PV technologies that we have now in research phase and also in the market, they can be they can be divided into 3 different technologies. So the first one is called first gen. So first gen is made of wafer-based crystalline silicon solar cells. And this first gen can be divided into 2. The first one is monocrystalline or single crystal, or monocrystalline silicon solar cells. The second one is multicrystalline silicon solar cells, where you have multiple grains on the wafer, and then the wafer is turned into solar cell as well. Okay. The second one is called second generation or second gen, which is made of thin film solar cells. The one that use material with much lesser in comparison to the first generation. Okay, I'm going to show you later on the details of each generation. And the third gen is also based on thin film solar cells, but they are aimed to produce high efficiency solar cell. Okay, so let's go through one by one. So this is first gen solar cell. So first gen, I said later just now, is made of monocrystalline silicon solar cell and multicrystalline silicon solar cell. So if you look at the monocrystalline silicon solar cell, you normally see a uniform color of the solar cell due to the presence of a single grain. So you don't see any boundaries, you don't see any grain boundaries anywhere in the wafer. And typically, if you talk about industrial build solar cells, so the width of this wafer or this solar cell is normally around 6 inch, right? 6 inch, 6 by 6. So on the other hand, if you look at multicrystalline silicon wafer or multicrystalline silicon solar cells, you can see clearly the grains in the solar cells, because the grains are formed during the growth of the multicrystalline silicon wafer. So the conversion efficiency of the monocrystalline is slightly higher than multicrystalline. Last time, a few years ago, I think about 5 to 7 years ago, multicrystalline was more dominant because it's cheaper than monocrystalline. However, due to the reduction of the cost of the monocrystalline silicon wafers and solar cells, multicrystalline now has lower and lower market to serve, because the technology cost of monocrystalline is already comparable to multi with better efficiency. Okay, so you can see here the description. So both wafers, either mono or multi, both of them use thickness of about 170 micron now in the industry. So this 170 micron is somewhere about twice of our hair thickness. So usually our hair thickness is somewhere around 80 to 90 micron thickness. So if you take one, and then the thickness around the thickness of the hair is somewhere about 80 to 90 micron. So this is about twice of our hair thickness. And in fact, it's going lower in terms of the wafer thickness. In the projection of ITR PV, National Technology Roadmap for PV or ITR PV, so it's projected that the wafer thickness will be reduced over time. So perhaps it's going to go down to around 100 micron. So we'll see that perhaps in a couple of years. So for this first gen, the efficiency ranges from 18 to 25 typically, and the technology lasts for 25 years in the field. So this is the most dominant technology that we have in the market right now, which represents about 90% of the whole market. I'm going to show you later on. So this is an example of monocrystalline silicon solar panels laid on a roof of a building. So normally, if you talk about a one solar panel, they normally have 60 or 72 solar cells. If you talk about 60 cells panel, then normally you can see 5 by 12. Then that will form 60 cell panel. So on the other hand, if you look into 72 cells panel, so that's normally a late in the form of 12 by 6. Okay. So second generation technology now. Second generation is thin film solar cells, usually deposited on foreign substrates, because if you reduce the material that you want to use for the PV conversion, the material will get more and more brittle if you go lower and lower. So just imagine if you reduce your wafer thickness, 170 micron just now, to only about 1 to 10 microns. So they're going to break easily because they're going to be more and more brittle. So that's why for this particular technology, the solar cells need to be deposited on foreign substrates. For example, glass substrates or plastic substrates, or even cloth, in order to enable thin film solar cells, and they can be flexible as well. So normally they have 150 to 200 fold reduction of material consumption. So this is in fact the aim of the technologies, because we want to reduce the material that we use for the PV conversion. Because sometimes 10 years ago, the cost of the first gen was like $2 per watt, and the cost for thin film technology is way lower than that. So due to the economies of scale for the first generation, the technology cost of the first generation has gone down to be comparable with the second generation. So now companies manufacturing second generation solar cells find it more difficult to survive in the market, because the technology cost for the first gen has reduced tremendously. Okay, the efficiency of the second generation ranges from 10 to 15%. So for examples, we have amorphous silicon for this that we normally see on our calculators or watches, wristwatches. We have a cadmium telluride, or we call it CDTE. This one manufactured by First Solar. We can also use compounds like CIGS, copper, indium, gallium, selenide solar cells. We can also use CZTS, or copper, zinc, tin, sulfide solar cells. So they are compound-based solar cells in nature. So in comparison to silicon, for example, amorphous silicon. So if you look at this second generation, you can use elemental material like amorphous silicon, or it can be a combination of cadmium and telluride to form cadmium telluride. It can also be quaternary like CZTS. So this is an example of amorphous silicon solar cell. So it can be deposited on glass, for example, you can see down here. And on the other hand, it can also be deposited on plastic to make flexible solar cell. So this is an example of cadmium telluride solar cell manufactured by First Solar. This is what we have in Malaysia as well. So you can see here the cadmium telluride, the main absorber layer, which absorbs the incident light, is sandwiched in between a couple of layers. So the light is coming from the front. So in this illustration, in this device architecture, we call it as a solar cell based on superstrate orientation, because the incident light has to go through the glass substrate in order to reach the device. So we call this one a superstrate configuration. On the other hand, we may also have another configuration which the sunlight hits the device directly, and the glass sits at the back of the device. So that's called substrate configuration. So this way is called superstrate configuration. So we have cadmium telluride to do the light absorption. We have cadmium sulfide on the front side as a window layer, a very thin one, 200 to 300 nanometer, and cadmium telluride is usually 2 to 5 micron. In the 2 to 5 micron as the absorber layer. And then we also have back contact at the back. Right, we also have third generation. Third generation is based on organic or perovskite solar cell, and also dye-sensitized solar cell. We may also use quantum dots in the solar cell. And usually the film thickness for this technology is 300 to 500 nanometer. So now it represents a small market, because we only have a couple of startups that just commercialize the technology. So perovskite is a new emerging technology. So the conversion efficiency has just hit 25% world record for a single junction. So however, we have stability issues in the perovskite due to degradation of the material upon exposure to temperature and humidity of the atmosphere. So it's still under intensive research in order to be feasible for mass production. So this is another examples of a third generation perovskite cell. So this is the one commercialized by Solar Technologies in Poland. So you can see the solar cell is prepared on plastic substrate on the left and on glass substrate on the right. Okay. And the structure is based on methyl ammonium, or we call it MABX3, where the conventional perovskite technology use methyl ammonium lead iodide structure, MABX3. On the right hand side, you can see the absorption coefficient of the perovskite solar cell in comparison to others. So CH3NH3 PbI3 is the methyl ammonium lead triiodide. You can see the absorption coefficient here is very high in the visible region, particularly if you want to compare with the dominant one, the silicon one. So silicon is way lower in terms of absorption coefficient due to its indirect band gap nature in comparison to perovskite. So that's what makes perovskite very interesting. So this is another example of perovskite, but this one, the perovskite is coupled with silicon in tandem junction or in double junction, where perovskite is placed on top of the silicon solar cell in order for us to absorb more sunlight. If we use silicon alone, then the theoretical efficiency of the conversion will be somewhere around 29% due to the limitation of the band gap of silicon. In order to break 30% conversion efficiency, we need to use another layer on top of silicon in order to break the glass ceiling of 30%. Okay, so the latest world record by Oxford PV, a spin-off by Oxford University, now running mass production in Brandenburg, Germany. So they just reached the conversion efficiency of 9.5% for tandem perovskite on silicon solar cells. So this only, yeah, this is back in December 2020, so still new. Okay. Right. Another third generation is called organic PV. So organic PV is something that you can see here. So it composed of a polymer active layer and sandwiched by electron transporting layer on the front side, on the rear side, sorry, in this case, and hole transporting layer. So you need to have electron transport layer and hole transport layer, and then normally it's deposited on glass and or plastic. Okay, so you can see here an example of flexible organic solar cell, and this is a roll-to-roll process which enables fabrication of flexible solar cells, which is lower in cost in comparison to other processes. If you look at the PV technologies now in the market, so this is the top 10 of PV module manufacturers in 2020. So you can see here from the 10 manufacturers, only one is based on thin film solar cells. So only 1 out of 10. So all other 9s are based on silicon wafer technology, right? Silicon wafer technology. So you can see here at least, so that's about 80%. 80% of the list here is dominated by China or Chinese companies. So for example, Longi, Jinko, JA, Trina, Canadian, Ryzen, CHNT, and also Suntech. So right, only Q Cells and First Solar are not from China. So for Malaysia, so we have quite a number of giant manufacturers in Malaysia. We have Jinko, JA, Longi, SunPower, Q Cells, Panasonic, and also First Solar for the manufacturing of solar cell. So if you look at the technologies by production, by market share, the data from 2018 here shows that 90% of the PV market is dominated by crystalline silicon solar cells, composed of multi and mono technologies. and only the small chunk here, the top one, is by thin film technologies, mainly cadmium telluride by First Solar. So that shows the domination of the crystalline silicon in the PV market right now. So why crystalline silicon base? Why is it so dominant? There are a few reasons for that. The first one is silicon is abundant in the form of silicon dioxide in our Earth crust. And then we have extensive knowledge from microelectronics industry, so which has been around for 50, 60 years at least. So we've learned a lot on silicon because our chips in the phones and in the laptops, the transistors are made of silicon as well. So silicon has a near ideal band gap of 1.1 for conversion process, which is ideal at 1.4. So it's not far away from the ideal conversion efficiency as far as the band gap is concerned. And silicon is non-toxic if you compare to perovskite, which contains lead, for example. Okay, silicon has high efficiency, so now the world record has reached somewhere 27%, right, for lab scale cells. And for the module, for the panel size, for the panel, the big size, the efficiency record is somewhere about 24%. And silicon has reduced technology cost over time. I'm going to show you later on. So this is the band gap. If you want to know the solar cell conversion efficiency, the theoretical limit is defined by Shockley-Queisser limit for single junction solar cell. So it shows a semiconductor band gap on the x-axis and the theoretical limit of the solar cell on the y-axis. So you can see here that if you talk about the standard solar spectrum, AM 1.5, so the peak is somewhere around 1.4 electron volt, right? So that's one of the reasons why cadmium telluride is used, because the band gap is somewhere about 1.4 to 1.5. And silicon is somewhere here, 1.1. It's not far away from the ideal band gap for conversion. And coupled with these previous reasons, so that makes the silicon-based solar cells dominant in the market. So this is the best research cell efficiencies, or the world record cell efficiencies maintained by NREL, or National Renewable Energy Laboratory. You can search on the website, and you can see right away the world record cell. So you can see various technologies on the chart, from silicon-based solar cells on the blue with the blue legends, and we also have emerging technologies in red, composed of dye-sensitized solar cell, perovskite, tandem cells, and quantum dots, and whatnot. And you also have thin film technologies like CIGS, cadmium telluride, amorphous silicon, and technologies with multi-junction. So technologies which use more than one PN junction in stack in order to harvest a broader spectrum of sunlight. So solar is now cheapest electricity in history, confirmed by IEA, late 2020. So you can look at the details here in World Energy Outlook of 2020, the report. So we can see here on the chart the plot of the technology cost of solar from 1976 down to 2019. So we can see here in 2017, the cost of the solar is somewhere $100 per watt. So that was super expensive. Okay, so due to the learning curve, due to economies of scale, increased conversion efficiency, and maturity of the technology, improved technology know-how, and more companies producing more and more solar cells, and we learn a lot from that. The technology cost has reduced to somewhere less than 30 cents per watt in 2020, right? So that's a huge learning curve with a little fluctuation here and there along the way. So if you want to talk about opportunities for chemistry students, so in the field, in the PV industry, you can divide the field mainly by upstream and downstream. So upstream on the left and downstream on the right. So upstream mainly consists of R&D and manufacturing of the material, of the cell, of the module. And then downstream is more related to the application, installation, system integration of the PV panels. So R&D and manufacturing here, in the circle here in the upstream. So opportunities for chemistry and physics students is mainly here. So for the polysilicon wafer cells and modules, so this is not limited to crystalline-based silicon solar cell, because I picked this chart from the silicon-based industry. So that's why you see polysilicon wafer cells and modules. So but this upstream and downstream value chain is also applicable to technologies like organic or perovskite solar cells and whatnot. So if you are interested to join this field, then opportunity will be related to the R&D and manufacturing of the technologies, right? Rather than the downstream, because downstream is more engineering of the technologies, which is mainly mechanical, electrical, civil, and stuff like that, right? So a little bit on the applications, which might be relevant to you as well as far as opportunities are concerned. So this is one image of our largest solar farm or solar park in Malaysia, just started operation. So the size is about 50 megawatts. So it's gonna be expanded. So when you talk about solar farm, the typical range is somewhere tens of megawatts up to hundreds of megawatts, depending on the scale that we have. So another opportunity would be for rooftop solar, where you can use the space on the roof to harvest the sunlight. So this is an example on residential and commercial building. So the commercial is on IKEA here, we have in Malaysia. So the range is typically from kilowatt to megawatt, depending on the space that we have for the installation. So this installation can be optimized in the form of self-consumption for the residential and for the commercial application as well. So you can use the energy generated on the roof for your self-consumption, or it can also be exported back to the grid based on the tariff or the package that you have in the country. Another application would be on the solar windows and facades. So we call this one as BIPV, or building integrated photovoltaics. So you can see here windows. We have so many windows that we can use for application of solar cells. So in this case, normally the conversion efficiency is not that high, because if you talk about windows, then you want to have some natural light to get into the building as well. So it will be a trade-off of conversion efficiency or light that you can absorb versus light that you want to come in, because the moment you want to generate more light, you want to have more light coming into the building, so you will compromise the light absorption because you will need more transmission. So in the solar cell, transmission represents as an optical loss. Okay. So also, if you want to use the applications as PIPV, so you have to have aesthetics element as well. So you need colors, and you need the designs and stuff like that. So that will somehow compromise the efficiency of solar cell as well. So it's a juggle between the conversion efficiency and the purpose and the specific application. So another new one is called indoor PV. You can use indoor PV, indoor solar cells with small power, in order to power low power devices such as Wi-Fi or smart homes or sensors inside the house and stuff like that. So the typical range of the power produced by solar cells in this case is nanowatt to watt, nanowatt to nanowatt range. And instead of using sunlight as your illumination spectrum, as your incident light, we can use incandescent lamp or compact fluorescence or white LED even, in order to power the solar cells for indoor PV application. Yeah, so that's it from me for this sharing session. So this is my contact number. So my email is also included, and my YouTube and LinkedIn are also available down here if you want to be in contact. So that's all from me. Bye-bye. I hope you learned something from this sharing session, and enjoy. Bye-bye. Take care. Stay safe.